Hello everyone. In this video, we are going to discuss the concept behind shear and bending moment diagrams. If you have been having difficulties understanding shear and bending moment diagrams, then stick with me because at the end of this video, you will fully understand the concept behind shear and bending moment diagrams. Now let's start. Shear and bending moment diagrams are two of the most important tools in determining the internal forces in beams or columns. So the whole concept behind shear and moments is to be able to assess bending stresses. They graphically display the shear forces and bending moments in a given flexural element. Now, we can draw a shear and moment diagram very quickly if we can recognize some of the relationship between those quantities. Now let's say if we consider a beam with a variable load, this will be any arbitrary load. Let's say some load W. It can be of any magnitude, and this load is drawn positively, meaning it is going upward. Now, if I cut a little slice out of the beam and I call it ds, that is small ds, we will say the load might probably varies across the beam. But across the little differential element ds, that is the small slice we cut out of the beam, we are assuming the load is constant. Now from one end of the segment, that is the little ds, to the other end, there is a change. From the left side, we will have a shear force V, and this is small v. Then on the other end, we will have a shear force plus some change in shear dV. Also for the moment, on the left side of the cut, we will have a moment, while on the right side, we will have a moment plus some change in moment dm. So the idea is, from one end of the small segment ds, we will have a little bit of change in shear and a little bit of change in moment. After that, we will use equation of equilibrium to determine how much the small segment dv and dm changes from one end of the segment to the other end. So we are going to calculate the small dv and small dm. Now, if you take a look at the screen, we have the small segment we cut out from the beam. The length of the small segment is ds, as you can see over here. So we want to determine dv and we also want to determine dm. So first of all, let's determine dv. Now, how can we determine dv? We are going to use equilibrium. So we are going to say summation of all the vertical forces is equal to 0. And we are going to say all the forces acting upward is positive, while all the forces acting downward is negative. On the left side of the cut, as you can see, we have the shear force acting upward. So this is going to be positive. So we are having V. Then on the right side of the cut, we have the shear force acting downward, and this is V plus dV. So because it is acting downward, it is going to be negative. So this is negative V plus dV. And make sure you introduce your parentheses. Lastly, we have the distributed force W, and this is acting upward. Because this is a distributed force, we need to multiply the quantity of the force by the distance, because this is distributed over the length ds. So because it is acting upward, it is going to be positive. So this is positive W, then multiply ds. So we don't have any additional vertical force, so this is equal to 0. So now this is V. The negative is going to multiply everything inside the parentheses. So we have negative V, Then negative multiplied positive is negative. This is negative dv, then plus wgs is equal to 0. So the v's are going to cancel out. So we are left with negative dv plus wgs. So if we take this, if we move this to the right side, we are basically going to have dv is equal to wgs. So this is the value of dv. So now let's calculate the value for dm. So how can we calculate the value for dm? What we are going to do is we are going to take summation of moments either on the left side or on the right side, and we are going to equate this to 0. So I'm going to take summation of moments on the right side, and this is equal to 0. So this is summation of moments on the right side is equal to 0, and we are going to say all the movements acting in the counterclockwise direction should be positive, while all the movements acting in the clockwise direction should be negative. So on the left side of this chord, we have m, and this is acting in the clockwise direction, so it is going to be negative. So this is negative m. Then on the right side, we are having m plus gm. So this is acting in the counterclockwise direction. It is going to be positive. So this is positive m plus gm. So because we know that moment is equals to force times distance, so we also need to take a look at the forces. So on the left side, we have the shear force acting upward, and if we apply this force here with relative to this point, it is going to try to rotate this in the clockwise direction. So because of that, we are going to have negative. So this is negative. So the shear force is v, then multiply by the distance. So what is the distance from v to the point of origin? That is the point we are trying to take the moment. This distance is ds, as you can see. So this is v, then multiply by ds. So we are not going to have any moment here because this shear force is producing no moment, because this is acting at the point of origin. That is the place we are taking the moment. So there will be no moment produced for this shear force. So now, if you take a look at the load, we have a distributed load of W, and this is acting upward. So because this is a distributed load, we need to decompose this load into point load. And how can we do this? It is basically the magnitude of the load, then multiply by the distance. So this is basically W multiply GS, and this load is going to be acting at the middle because we are having a rectangle. So it's going to be W then multiply S. So this is the load. So now if we try to apply this load WS that is located at the middle of this small segment with relative to the point of origin, it is going to try to rotate this small segment in the clockwise direction. So we are going to have a negative value. So this is negative WS. So this is the force. So we also need the distance. So what is the distance from WS to the point of origin? So it is basically going to be half of ds. So it's going to be ds over 2. So this is the distance from here to this point is ds over 2. So this is multiplied by ds over 2. So we don't have any additional forces. So this is equal to 0. So now the n are going to cancel out. Then we now have gm, then minus vgs, then minus w. So this is going to be wgs squared, then over 2 is equals to 0. So now, because we know that ds is infinitely small, we know that ds is infinitely small. So because of that, we can cancel out this ds because we took a small segment of ds out of the beam. And if we square something small, it is going to give us something infinitely small. So because of that, we can just ignore these values here. We can ignore this because this is infinitely small, so we don't need to consider this. So we can ignore that. So after that, we are going to get gm minus vgs is equal to 0. So because we want to find the m, so we can just take negative VDS to the right side. So dm is going to be equal to VDS. So this is the value of dm. dm is equals to VDS. Now we can rearrange this to get the load equation and the shear equation. So if we rearrange this, we are going to get the load equation, meaning we are going to solve for W. So we are going to get W is equal to dV over ds. So this is the load equation. Also, if we rearrange this, we are going to get the shear equation by solving for V. So this is going to be V is equal to dm then divided by ds. So we have the load equation. This is the load equation. Then we have the shear equation. Now we have a relationship between load, shear, and moment. If I want to determine the shear, I can just integrate the load diagram. If I also want to determine the moment, I can also integrate the shear diagram. So for the shear, it is going to be the integral of W ds, while for the moment, it is going to be the integral of V, which is the shear, then multiply ds. So if we are looking at the relationship between load and shear, we can say that at any given point, the slope of the shear diagram is equal to the load because dV over ds is the derivative or slope of the shear diagram. And also, between the 2 points, the change in shear is equal to the magnitude of load between those 2 points. Same thing is true for the moment. At any given point, the slope of the moment diagram is equal to the shear. So this is dm over ds is equals to v. And between 2 points, the change in moment is equal to the area of the shear diagram between those points. So because we are dealing with areas, we can draw shear and bending moment diagram graphically without using calculus. So we will see how to draw shear and bending moment diagrams later on, and this is going to be in my next video. So if you want to see that video, make sure you subscribe to the channel by hitting the red subscribe button below this video and click the bell notification icon to get notification whenever I upload a new video. Bye bye.